Krishna sir, can you hear me?
Yeah, I can hear you. Please start.
Okay. So before we begin the session, just a gentle reminder. I request all the participants to keep yourself mute until we finish the session. And also you have a Q&A round wherein you can ask your queries once sir has completed his talk. And this session is being live streamed on YouTube so that you can watch it there on a later date as well. So good evening and a warm welcome to Dr. Krishnakumar, our esteemed speaker. Krishna sir is here to share his insights on the challenges in solid and liquid waste disposal and management, one of the YIP themes for ideation. A special greetings to all the students from colleges across Kerala who are enthusiastic about innovation and also who wants to make a meaningful impact. So to formally commence the talk, I invite Ms. Nasla, the district coordinator at YIP KDISC, to introduce our esteemed speaker and extend a warm welcome. So over to you, Nasla.
Thank you, Asmi. Am I audible?
Yes, you
Yes,
are.
yes.
Okay. So hi, ഞാൻ അസ്ല. ഞാനിവിടെ എറണാകുളത്ത് ഡിസ്ട്രിക്ട് കോർഡിനേറ്റർ ആയിട്ട് അറൌണ്ട് 1 year ആയി വർക്ക് ചെയ്യാൻ തുടങ്ങിയിട്ട്. സോ ഇപ്പൊ നമ്മൾ 6th എഡിഷൻ YIP നമ്മൾ സ്റ്റാർട്ട് ചെയ്തിട്ടുണ്ട്. അപ്പൊ അതില് കഴിഞ്ഞ എഡിഷനിൽ നമ്മൾ 24 ടീംസ് ആണ് ഇൻട്രൊഡ്യൂസ് ചെയ്തിട്ടുള്ളതെങ്കിൽ ഇത്തവണ നമ്മൾ 27 ടീംസ് ആണ് ഇൻട്രൊഡ്യൂസ് ചെയ്തിട്ടുള്ളത്. അപ്പൊ ഓരോ ടീംസിനെയും അതിന്റെ ചാലഞ്ചസ് അതിലുള്ള ഗൈഡ് ഒക്കെ ചെയ്യാൻ വേണ്ടിയിട്ട് നമ്മൾ എപ്പോഴും ഈ തീമാറ്റിക്കൽ ടോക്സ് നടത്തുന്നുണ്ട്. അപ്പൊ ഇത്തവണ നമുക്ക് ഇവിടെ നമ്മൾ തീമാറ്റിക് ടോക്കിൽ സോളിഡ് ലിക്വിഡ് ഹസാർഡിയസ് വേസ്റ്റ് മാനേജ്മെന്റിൽ വന്നിട്ടുള്ളത് ഡോക്ടർ കൃഷ്ണകുമാർ സർ ആണ്. അദ്ദേഹം യൂണിവേഴ്സിറ്റി ഓഫ് കേരളയിൽ നിന്ന് മൈക്രോബയോളജിയിൽ PhD കംപ്ലീറ്റ് ചെയ്തിട്ടുള്ളതാണ്. ഓൾസോ നാഷണൽ ഇൻസ്റ്റിറ്റ്യൂട്ട് ഫോർ എൻവയോൺമെന്റൽ സ്റ്റഡീസ് ജപ്പാനിൽ നിന്ന് അദ്ദേഹത്തിന്റെ പോസ്റ്റ് ഡോക്ടറൽ റിസർച്ച് കംപ്ലീറ്റ് ചെയ്തിട്ടുള്ളതാണ്. സർ അറൌണ്ട് 2004 നിസ്റ്റിൽ ഒരു സയന്റിസ്റ്റ് ആയിട്ട് ജോയിൻ ചെയ്തിട്ടുള്ളത്. ഇപ്പൊ സാറ് നിസ്റ്റിലെ എൻവയോൺമെന്റൽ ടെക്നോളജി ഡിവിഷനിൽ സീനിയർ പ്രിൻസിപ്പൽ സയന്റിസ്റ്റ് ആയിട്ട് വർക്ക് ചെയ്യാണ്. He's leading the environmental cleanup research programs, and he is also a professor at CSIR Academy. He's a recipient of CSIR research grant for his PhD research. He's also got 4 international patents granted, and one of them is published. He's published papers and is a research guide. His major research areas are biological waste treatment systems, on-site treatment systems, waste valorization, bioremediations, etc. സോ ഒരു എക്സ്പേർട്ട് ആണ്. ഇത്രയും ക്വാളിഫിക്കേഷൻസോട് പറയുമ്പോൾ തന്നെ അറിയാലോ സാർ ഈ ഒരു ഏരിയയിൽ ഭയങ്കര എക്സ്പേർട്ട് ഉള്ള ആളാണ്. അപ്പം കുറച്ച് സമയത്താണെങ്കിലും ഒരു 1 hour കൂടെ സാറിന് നമ്മുടെ സ്റ്റുഡൻസിനെ ഹെൽപ്പ് ചെയ്യാൻ വേണ്ടിയിട്ട് വന്നതിൽ വി ആർ ആക്ച്വലി വെരി ലക്കി ടു ഹാവ് യു ഹിയർ. സോ വാം വെൽക്കം ടു സാർ ഈ സെഷൻ ഹാൻഡിൽ ചെയ്യുന്നതിന്. ആൻഡ് ഓവർ ടു യു സർ.
Thank you, Nasla, for your kind introduction. At the outset, am I audible?
Yes, sir, you are audible.
Yeah. So at the outset, let me thank KDISC and the organizers of KDISC for inviting me for this program and giving me an opportunity to interact with the student community. And I also thank all those joined this online session. I appreciate your interest in solid and liquid waste management as well as hazardous waste management. And without further introduction, I will share my slides. Is it visible now in PPT mode?
Sir, it's not in, PPT is visible, not in presentation. Yeah, it is visible now. Yeah, it is done, sir.
Okay. So the title of my talk is given something like solid and liquid waste management, disposal and management, especially the scope and challenges for the young innovators or entrepreneurs who are looking forward to take up this sector as a future career. So the waste management as such is a very broad umbrella term, and the content in which we cannot cover in one session or a couple of sessions. So therefore, what I have done today is I'll be talking, or I'll be limiting my talk only to certain areas only, like this. I'll be talking on solid waste management. Even solid waste management itself is a very broad term. In today's session, I'll be talking only on organic waste treatment, which is the major fraction of municipal solid waste, or which is a major fraction of our household waste, which are more familiar to us. And there is a problem in managing and disposing the organic fraction of waste material at a household level. So I'll be talking a little on solid waste management. Then I'll be talking a little on liquid waste management. Again, not on any industrial effluent treatment, but on community level wastewater treatment. The wastewater we all dispose from our house. How are we disposing it properly? Are we treating it properly? If we are not treating it properly, what are the options before us? And those kind of things on the liquid waste management. And finally, I'll be talking also on how, say, NIIST, being a national research institute, how we can help you in entering into this tech. What kind of support as a research institute NIIST can offer? So these are the three main sections I'll be handling or I'll be delivering in this 45 minutes, and we can have a question and answer session after that. So as I said, to begin with, solid waste management, I mentioned we'll be talking only on organic waste treatment. So if you look at the composition of MSW stands for municipal solid waste, most of the fraction. So the most of the fraction is around roughly around 70% of the municipal solid waste is organic fraction or the food-based fraction. And the recyclable fraction will be around 15% of the plastic, paper, glass, electronic waste, all those things comes under that category. There'll be 10% inert material and biomedical waste that we have to consider separately. In fact, the hazardous waste comes under this biomedical category, and that comes to around 4%, and there is another 5 fraction that we are not considering. So this 70 fraction or 70% is a major component of the organic, major component of the municipal solid waste. And if you look at the different treatment options, internationally accepted or widely practiced different approaches for treating this organic fraction or the food-based fraction of solid waste, it's something like an inverted pyramid in which the top of the pyramid will have the most preferred approaches and the least preferred occupy the bottom of the inverted pyramid. You start from the least preferred approaches. The least preferred one is landfill or incineration. Unfortunately, this is being extensively practiced at many places. We are seeing that, but it is the least preferred approach for treating or disposing organic fraction of solid waste. And the second approach is composting. Composting is a very familiar term. I hope all of you may be knowing what is composting. And the end product of composting is nothing but biomanure or compost that we can use for the agriculture purpose. And the next option is industrial use. A better term is anaerobic digestion. And if you adopt anaerobic digestion, the end products, apart from manure, which you get in composting also, you will get one more product, which is the bioenergy, or what you call as biogas. And another approach is feed animals, feed hungry people, and source reduction is the most preferred approach. Definitely, we should reduce the source generating organic waste at the source. So composting and anaerobic digestion are the most widely accepted practice by which you can recover some valuable products from the organic fraction of waste material. Now, anaerobic digestion is, or abbreviated as AD, it's also known as the AD process, which is nothing but the biogas technology, most popularly known as the biogas technology. It is also known more scientifically as the biomethanation process or the anaerobic bioprocess, all the same. Anaerobic digestion, AD process, biogas technology, biomethanation, anaerobic bioprocess, all the same and one, nothing but the biogas technology, which is very familiar to all of us. Now, so this is a very broad picture of the scenario of organic waste-based energy recovery through the anaerobic bioprocess. This is a big, broad picture, an Indian scenario. So you start with the substrate or feedstock, which is nothing but an organic waste material, which can be organic fraction of municipal solid waste. It could be secondary slides from sewage treatment plant. It could be agricultural residues. It could be farm waste, like that. Any organic waste material can be your start material for any biogas technology or recovering biogas or bioenergy from waste material. Sometimes you need to go for some pre-treatment, something like reducing the size, particle size reduction, mechanical grinding, size reduction, all those things comes here, pre-treatment step. Then it directly feed or goes to what you call the biogas plant or an anaerobic digester, which is nothing but the bioprocess, anaerobic bioprocess. And inside the biogas plant, a little bit complicated biochemical process happening. We'll come to the little details at a later stage of this talk. And the end product of biogas technology or anaerobic bioprocess, you'll get two things. One is a biogas, which it can be used for heating purpose, or you can recover power out of that, or you can even consider for a combined heat and power. We call it the CHP. So biogas is one product from the biogas plant, and the second product is digestate or slurry, which you can take for some downstream processing, and the end product is solid and liquid manure. And these solid and liquid manure, nowadays we collectively call it as the fermented organic manure. It's an excellent fertilizer. So up to this level, we are all practicing this in our household, a small-scale biogas plant. You're putting some kitchen waste into that. You'll be getting some biogas that you're using for some kind of cooking in your home, and you'll be getting slurry that you'll be diluting, and you'll be supplementing the plants or garden plants for as a manure. So up to this level, you'll be practicing. But when you handle waste material in tons quantities, like 500 tons or 3,000 tons per day, the scenario is entirely different, because the kind of or the quantity of biogas that you recover from those kind of huge biogas plants, that much biogas usage is there. Then there comes what you call as the compressed biogas or CBG or bio-CNG. So before producing the biogas, what you need to do is you have to upgrade the percentage of methane in the biogas, or what you call the purification step. The normal biogas will have a methane content of something like 55 to 65%. From that, we have to enhance the methane percentage to above 95% by removing impurities like carbon dioxide, hydrogen sulfide, ammonia, water vapor, and all those things. Thereby, you can increase the methane percentage. Then once you upgrade the methane percentage to above 95%, you have to compress the biogas for transportation purpose. Compress means you'll be increasing the pressure of the CBG, something like around 240 bars. You can imagine what is the pressure at 240 bars. They'll be transporting to different distributing centers or distributing location. It could be a fuel station or distribution, any outlets for distributing these compressed biogas. So at this point comes major schemes like the SADA scheme, which is a highly ambitious program of the government of India through the Ministry of Petroleum and Natural Gas. So what is SADA scheme? I'll be coming to the next slide. Apart from SADA scheme, there are major NGOs like the Indian Biogas Association. So these kind of agencies also play a major role in these kind of highly ambitious programs in our country. Now, I mentioned about SADA scheme. SADA stands for Sustainable Alternative Towards Affordable Transportation, which is initiated by Government of India in 2018 under the National Policy on Biofuel. As I said, it's a very highly ambitious program of Government of India. If you look at the major objectives of SADA scheme, are to utilize the bio-waste in our country to reduce import dependence on natural gas. You may be wondered to know we are producing only 7% of our total natural gas consumption. The remaining 93% we are importing from other countries. So the government wanted to reduce the dependence on our import on natural gas. For that, government wanted to promote these kind of programs. Then these kind of implementing these kind of plans at different locations in the country will obviously generate a lot of employment, both in rural and urban sectors. So employment generation is another agenda of this program. Then reduce environmental pollution due to burning of agri residues. So you may be knowing in northern part of India where thousands of hectares of lands are utilized for agriculture purpose, mostly for wheat and rice. So at the end of every season, there'll be huge quantities of residues or rubbles. They'll be burning it and leading to severe environmental pollution in northern part of India. So if you, instead of burning these stubble, if you recover highly valuable products like biogas, that can also reduce environmental pollution. So it is estimated that India has the potential for producing nearly 60 million metric tons of CBG and proportionally reduce our import dependence on energy import. And I hope you may be remembering the recently completed COP28 at Dubai. One of the main agenda of COP28 was transition out of our dependence on fossil fuel, considering the adverse climatic change due to the excess use of fossil fuel. Because of that scenario, also we need to look for alternate energy sources like biogas or bioenergy. So under the SADA scheme, a total of 5,000 CBG plants have been envisaged by Government of India by 2025. That will produce nearly 15 million metric tons of CBG per year. And by the end of this 2024 December, government has planned to initiate at least or commission at least 100 CBG plants at different locations in India. And many plants are in the commission stage at different locations in India. And the total investment in the sector is about 1.75 lakh crore. And the average project cost is around 35 crores. Apart from all these things, the capital subsidy support to 100 crores available from MNRE, so Ministry of Non-Controllable Energy Resources. So all these government supports are to promote these kind of major programs. Not only that, the Reserve Bank of India has identified the CBG plant one of the priority sectors, and government subsidies, government loans, one different national banks are available for initiating these kind of activity. And then if you produce huge quantities of CBG, off-take support available from oil marketing companies. So all these promotional offers are available from the government to support these kind of activities. Last year, November, Government of India made it mandate that phase blending of CBG with piped gas to houses and CNG to the transport sector. So next time when you go to any fueling station, you please notice you see some board like this, Indi Green. You just remember that it is nothing but compressed biogas. So compressed biogas and CNG more or less the same, both can be used, just like the other. So I mentioned about the Biogas Association of India, a major NGO playing in this sector. So they have put up a request to the Government of India for the another end product, apart from the CBG, another end product is the fermented organic manure, which is nothing but the slurry. So the fermented organic manure from CBG plants off-taking by fertilizer manufacturing companies, which is a proposal from the Biogas Association of India. They are positively looking forward for a response from the government, because if the fertilizing manufacturing companies come forward to take this fermented organic manure, that will also add value to the one of the other end product from these kind of systems. Now, if you look at the number of CBG plants in India until March 2023, 48 running CBG plants in different states. You can see Gujarat stands foremost with nearly 30 numbers of CBG plants. And unfortunately, in Kerala, so far, we don't have any CBG plants. And probably you might have heard about one plant going to come in Ernakulam at Brahmapuram by BPCL. So this is one CBG plant in Tamil Nadu, which is in Namakkal. It was initiated by Indian Oil Tankers. Now it is operated by the Adani Ventures. You can see how it looks. It's spread a whole area of 17 acres of land. So what you see here are the biogas plant where the biogas is produced. They have 4 digesters or the actual biogas plant, which is total volume of 16,000 meter cube. And the design capacity of this plant to handle around 400 tons of organic waste daily. And from these biogas plant, from 400 tons waste material daily, they're producing around 36,000 meter cube of biogas. And after purification and compression, they end up with nearly 16 tons of CBG. Apart from the CBG, they also produce around 8,000 tons of organic manure, the fermented organic manure I mentioned previously, and they're selling it the brand name Aishwaryam. So I said the purification of biogas, where you'll be removing carbon dioxide from that, you end up with enriched carbon dioxide, which has high industrial value. That also they're selling it up. So a product like the CBG, the organic manure, and high purity carbon dioxide for industrial application. So many products you can recover from this kind of huge plants. And if you look at the capital and operational expenditure of these kind of big plants, so this graph will tell you the result. It'll tell you the details. So the approximate cost for a 5-ton CBG plant will be around 20 to 25 crore. And I have shown here the different breakup of this 20 to 25 crore. So the 36, nearly 40% of the cost will come for the biogas upgradation and compression purpose, 36% for the construction of the anaerobic digesters, 13% for the feedstock, the waste material procurement and transportation, 7% for online monitoring and sensors, and 4% for biofertilizer process. So that's about the capital cost and operational cost or the running cost for a 5-ton per day plant will be around 2.5 to 4 crore. There again, the major share, 26% is for the consumable cost, mostly for the raw material and other things. Labor cost, manpower cost for maintaining the plant, 20%. Again, you see the other fractions also. So it's a big business. So not only big plants, even small plants is also possible. So far, I was talking about big plants handling several tons of waste material. This is a comparatively small plant, which is operational in IIT Delhi campus. They're handling around 250 kilo of organic waste from their campus, mostly from the canteen. They operate with a single digester. The CBG production is only 25 metric. And whatever CBG produce, they are using it for fueling two-wheelers and four-wheelers within the campus. Apart from the 25 metric cube of CBG, they also produce nearly 25 kg of organic manure. And the installation cost for 25 kg handling CBG plant, as per their details, what they have provided is 35 to 40 lakhs. Now, so if you look at the CBG yield from a different feedstock, so as I said, the municipal solid waste will give you, this is the biogas yield. So per ton of municipal waste, you'll get around 85 metric cube or 85,000 milliliters of biogas. And if you go for purification and compression, the CBG you can expect is only 34 kilo. And for 1 ton of CBG, you need nearly 39.5 tons of waste material. And if you consider cattle dung or farm manure, it's slightly less. And like powder liter, slightly higher, press mud again in the same range, plus paddy straw is slightly on higher side. It depends on what is the biogas yield and all those things. So this is the BIS standard for the specification of CBG in India. As I said, the methane percentage minimum should be 90%. The mix of CO2, NO2, and oxygen, maximum permissible limit is 10%. CO2 alone cannot be beyond 4%. Oxygen alone should not be beyond 0.5%. Total sulfur, including hydrogen sulfate, maximum permissible limit is only 20 milligram per meter cube. And moisture content, the maximum permissible limit is 5 milligram per meter cube. Now, if you look at the multi-benefits of bioenergy recovery from biogas or bio-waste, as I said, the sustainable energy recovery, cut down greenhouse gas emission, and you can earn a lot of carbon credit out of that. Carbon credit, it's a very broad topic. We're not going into the details of that. And it's, of course, a sustainable waste management practice, and it will also support in sustainable food production through the use of organic fertilizer replacing the chemical fertilizers. So having said this broad picture, I'll take you to attention to this table, so which is a data from Kerala Shujitva Mission, sanctioned decentralized waste treatment units until 2019. You can see, so Shujitva Mission is one of the nodal agencies in Kerala. They're promoting a lot of waste management practices through different subsidies and all those things. So until 2019, if you look at the total number, nearly 16 lakhs of different units they have promoted through subsidies and all those things. And out of that, 90% of all the treatment units are in the composting sector. Only 10% is in the biogas sector. And if you look at the status of these biogas plants, unfortunately, many of these biogas plants are failed or they're abandoned. You can see large number of even household level biogas plants. Many of the biogas plants are failed and community level biogas plant. You can find n number of biogas plants at many locations in Kerala. They failed because of many reasons. So if you look at biomethanation based energy systems, In fact, biomethanation is not a new technology, it's an age-old technology, which is inspired from nature. What is happening inside the stomach of ruminant animals like the cow, sheep, or whatever it is, they take organic residue as grass or whatever it is, they process within their stomach, they produces dung, which is nothing but the organic manure. And you may be knowing it is also releasing a lot of methane into the air. A mature cow approximately releases 70 to 120 kg methane per year. And inspired from this what is happening in nature, people have developed technology. So these are early designs of the biogas technology, popularly known as the KVIC model or the Deenabandhu model, to latest advanced design where community level huge biogas plant handling tons and tons of waste material, producing large quantities of biogas, and from which they're generating electricity, power used for many applications, including heating, electricity production, all those things. So this is how the technology development happened. And this is a conventional biomethanation system, or what you call the biogas plant, which is very common in our places. We did a comparative study of how the performance of these biogas plant a couple of years back. And what we found is that these biogas plant will give you something like 60 to 140 liters, 145 liters of biogas per kg of food waste material you add into the system. And so this is conventional, the same thing. The previous image, same thing only, single unit. And what you do is you'll be adding the waste material here. Something is happening inside, and the biogas get collected here. The discharge slurry or the manure, as I mentioned, will be coming out through. So if you look at the detail of the thing, so this is the same port here. You'll be adding the waste material here, directly got inside. There are microorganisms that act upon the waste material, convert that into biogas. That's getting collected here in this dough. As more biogas get accumulated here, due to the buoyancy, it floated up. And you'll have a pipeline here, which directly connected or deliver the biogas to the stove. And the slurry will be coming out through this port. And there are certain inherent drawbacks with this conventional technology, because along with the waste material, you need to add water into the system. And there are restrictions like you should not add certain food fractions like eggshell, lemon, onion, all those things. You should not add, like guidelines are there. And there is every possibility of mosquito breeding in these kind of treatment systems. And large systems, say handling 10 kg or 50 kg or even beyond that. So those kind of systems will be not like this modular or fabricated system. They will be in civil structures, big civil structures. And once it is failed, revamping or regenerating that will be a huge task. Even emptying the system it's very difficult. And not only that, these kind of systems, as I mentioned previously, often report failure, foul smelling, discharge slurry coming on, all those issues are there actually. So the commonly used kitchen waste biogas plants are adapted from the conventional gobar gas plant, which are designed for recovering biogas from cow dung. Cow dung is nothing but a digested organic residue. And if you apply the same technology or the same method for recovering biogas from highly complex waste material, which contains fat, proteins, which are very hard to digest, there comes the problem. That is why these inherent problems are coming. So there need to some kind of design improvements are required, or process improvements are required, so that you can have a better system. So one more thing I wanted to mention here, all these conventional kind of biogas plants so far I was talking about, these are called wet anaerobic digestion units. Why? Because along with the waste material, you will be also adding water. So that is why it is called wet anaerobic digestion. There is another type of biogas process or biogas technology, which is called a solid state anaerobic digestion, in which you don't need to add any water, only the waste material directly. So I'll be explaining that in my coming slides. Now, little science part of biomethanation. So you know what is biomethanation or biogas technology? You're putting organic waste material into a system, and you'll be getting biogas. And in fact, it is not that simple. So you're putting a solid waste material, which is nothing but a mix of carbohydrate, proteins, and fat. It undergoes a lot of biochemical changes, and finally, you'll be getting biogas, which is a mix of mostly methane and carbon dioxide. So don't get confused with too much these kind of detail. Just understand that during the process of converting this solid waste material into gas, lot of intermediates are forming. You just imagine there's a pool of organic acids, alcohol, hydrogen, carbon dioxide, and so on. All these things are ultimately or finally getting converted into biogas. So this is a microbial process. A lot of microorganisms are involved in this process. So normally we call these methane-producing bacteria. But in fact, it's a very totally wrong usage. We don't call them as bacteria. But of course, some bacteria are there. But the last step, the final step, which the methane is producing, which is done by an entirely different group of microbes, better call them as archaea. They're not bacteria. They better call them as archaea. Or preferably, you can call them as methanogens, those microbes that produce methane, methanogens. And these methanogens are highly sensitive to oxygen. They're highly sensitive to acidic conditions, and they're extremely slow growing. And because of these very unique features of these microbes, if you are not providing the right conditions, your biogas system will fail. And that is one of the major reasons why many of the biogas are failed. People operating the system, service providers, maintaining the system without proper understanding of the science of biomethanation, they end up with troubles in maintaining the system. So this is an electromicrogram of the archaea or the methane producing microbe, which is the actual microbe at the terminal step, which is producing the methane. It looks like this, something like a grape. All these individual small dots represent one archaea or one methane producing microbe. For example, this particular methane producing microbe is called as Methanosarcina. Like that, many different names of microbes are available that produce methane from organic waste material. So this is Methanosarcina. So the same thing, this is a fluorescent image of the same microbe, same Methanosarcina. It always found in aggregate like this. So what I'm trying to say is that the successful operation and maintenance of biomethanation system require qualified manpower, strong technical background. There I see the involvement or the participation of young innovators or entrepreneurs who are looking forward or who would like to take this as a career. There's a huge scope for people out there and who would like to enter into this sector. And there are many basic things one should know, starting from sizing the biogas plant, what is the type of biogas plants, how to start a biogas system, what should be the mode of operation, what are the early warning signals for a biogas failure. There are certain signals one should understand. Okay, your system is going to fail or your biogas going to fail. There are early warning signs. We should know about all those. Then only you'll be able to avoid failure of the entire system. And if it is failed, how to address a failed digester? How to address a failed digester and how to manage a long-term shutdown of a biogas plant. If you don't have anything to feed to a biogas plant, how long you can keep the biogas plant without feeding any waste material? And if it is maintained for a long time without any feed, how to restart? Can we restart it as such, or is there any protocol for it starting? And how do you address low temperature inhibition? In fact, low temperature inhibition is not a problem for Kerala, but it's a problem in North India where the sub-zero temperature level during December, January, February, the temperature will be sub-zero. And there, since this is a biological process, the microorganisms activity will come down. And at that point, how do you manage the system? How do you ensure vital nutrient? Just like the human takes vitamins and minerals and all those things, microorganisms also require. How do you provide all these things? In what form we can provide all these things? How can we enhance biogas yield? How do you enhance methane percentage in biogas yield? And how do you upgrade or enhance? That's what I said, enhance the methane level. So how do we valorize the discharge? Acid discharge or the digestivities is another product. How do you valorize? So these are some of the very basic questions, and we should have answer to these questions. Then only we can say that you are technically equipped to operate a biogas plant. And unfortunately, as I mentioned, large number of service providers are with a limited technical knowledge about biomethanation systems. And that's the main reason for the failure or abandoned biogas plant, which creates a very poor image of biogas technology. And the public acceptance of this kind of biogas technology is very, very poor because of this scenario. Now, if you look at waste to energy system in urban and rural scenario, you can consider different waste material. If you consider the urban area, organic fraction of MSW itself, 70% is more than enough, particularly the food waste. Or there's a huge business opportunity for youngsters to start companies or that can provide biogas technology or companies that can troubleshoot failed biogas. All those things you can consider. But the limitations that you may be facing will be people will be asking why when there are other options, because you may be knowing in cities, evening time, you may be seeing trucks coming in and taking food waste, telling that they're giving this for pig farms. So the hotel operators will ask you, we have options like sending it to pig farms. Why do we need to install biogas plant? So this kind of question you need to address. Then for installing a biogas plant, there'll be capital cost, there'll be maintenance costs. So how do we manage these kind of things? Then another problem will be the availability of space. I say for the conventional biogas plant, for a 50 kg system, you need to have certain space for installing treatment system. In cities, space availability is a big problem. And freshwater requirement for the conventional system, you need water. And where do you dispose the discharge slurry? So these are technical issues you need to address, or these are the challenges before you when you enter into these kind of things. So that's about the urban scenario. And if you look at the rural scenario, the waste material like the agro residues, farm waste, septage, fecal sludge, household waste, all are feedstock or raw material for running biogas plant. You can consider multi-feed or co-digestion in which you'll be mixing different waste materials together and feeding into the biogas plant. And this will be a major contribution for the energy sector in rural areas, because in rural area where biogas, the LPG availability, if it is limited, these kind of small-scale biogas plant can contribute significantly in the energy sector. And apart from the energy sector, it will also ensure better sanitation conditions for the people living in those areas. So this is a simple example of a different feedstock one can consider for biogas recovery. So in the solid waste category, as I said, the organic fraction of municipal solid waste, food waste, fish, meat, poultry, processing center, waste material, sewage treatment plant, primary and secondary sludge, fruit and vegetable storage, like that. So many things you can consider as waste material. And you can also consider, and this table will give you how much biogas one can expect from the different waste material. For example, from food waste, every kg of food waste, you can expect something like 40 to 120 liter. But if it is cattle dung, since it is already digested, the biogas yield is obviously less. Pig dung still higher than cattle dung. Poultry litter is still higher. Human waste, very little only, 20 to 30 liter per kg of human waste. Crop waste, 35 to 40 liters of biogas per kg waste. So this is about the solid waste material. And you can also consider liquid waste, like hotel and wastewater from hotel and restaurants, food processing units, bakery plants, slaughterhouse, dairy, textile industry. From the waste material or the wastewater from these industry sectors can also recover biogas through the anaerobic bioprocess. Okay, so I mentioned about the conventional wet anaerobic digestion, where I also mentioned there is an alternate option, which is the solid state anaerobic digestion, in which you will not be adding any water. And this is a comparative table in which I'm trying to bring out the advantages of a solid state anaerobic digestion unit. So this is a comparison. One is a wet, or which is a more conventional biogas plant. This is solid state system. So each system handling 50 kilo. You can see the size of the digester. So the conventional biogas plant, for a 50 kilo handling system, the size of the digester will be something like 7,500 liter. It will be a huge structure. Obviously, it will be a single structure. On the other hand, the solid state digester, it will be just 2,000 liter capacity. So it occupies very little space only. And water consumption. So water consumption, definitely we need to add for the conventional biogas plant. Some people recommend to add 1:1 ratio, whereas some people will recommend you to add a 1:3 ratio. So 50 to 150 liter water you need to add. Need not be fresh water, but sometimes if no other wastewater like wastewater from your kitchen, if it is not available, you need to add the fresh water. But for the solid state, there is no water addition. Whatever the 10 liter I have mentioned here is only for the final cleaning purpose. And if you look at the biogas yield, so the wet biogas system will give you a maximum of 140 liter, whereas the dry system you can expect up to 200 liters of biogas. And since you are not adding any water here, the discharge slurry volume will be very less, something like 80% of your inlet volume. Since you are adding 50 liter, you will get around 40 liters. But here, you see, you'll end up with a lot of discharge slurry, and the management of this much volume of discharge slurry is another problem. So this straight away tell you, compared with the conventional biogas plant, the solid state anaerobic digestion technology is many advantages. So this is a photograph of a solid state anaerobic digestion unit, which is entirely different from the conventional biogas plant, which is very familiar to all of you. It's look like this. As I said, this system is capable of handling 50 kilo per day, something like a cylinder fabricated in, you can fabricate either in MS or in SS. And 2000 liter capacity only. There will be a mechanical grinder here. You'll be grinding the waste material here. Directly it goes inside. So it will be migrating through this. There is no short circuiting here. The waste materials have to travel all the distance. So this is the port from where the discharge slurry will be coming out. So whatever biogas produced will be collecting in a high quality polymer balloon here. And there will be a small booster pump here. Even if your burner is at a long distance, it will deliver the biogas at a high strength so that it will burn that just like LPG. So inside, you'll have a shaft with a lot of blades like this. You have a motor connected at this point with some electromechanical fittings, which is operated the timer. Daily, it will be missing a couple of times, but the power consumption per day will be around 700, less than a unit per day. And whatever biogas produced, as I said, will be getting collected. So the capacity of this tank will be, as I mentioned, 2000 liter. Food waste up to 50 to 60 kg it can treat per day. And the biogas yield will be something like 9,000 liter per day. And the methane percentage, 63 to 68%. So this is a better option. So we work in this sector for quite some time. So these are some of the biogas plant of the same, based on the same technology we have installed at different places. So this is in our own institute campus. Whatever food waste we generate around 50 kg in our department canteen, we treat here. This is one unit we installed a couple of years back in Regional Cancer Center, Trivandrum. This is one unit which is operational in the Reserve Bank campus in Bakery Junction. This is fabricated in stainless steel. This system again installed almost 5-6 years back, working perfectly well without any problem. Those who are interested can visit and see how it is working. And this is again 50 kilo. This is a small unit which we installed for the Themeatic government school. It's a very small unit actually. This is again 50 kilo per day. So what I'm trying to say is that all these units have proven many advantages compared to the conventional biogas. All these units 5 to 50 kilo. But we have also installed large capacity. Now for a 25 apartment building, which is expected to generate around 50 kilo food waste per day. So this kind of a system will be enough. It occupies only 4 square meter area. It produces around 9,000 liter biogas and 40 liters of organic manure. And the installation cost, there's a type error, it will be around 5 to 6 lakhs, the installation cost. But if you account the biogas and organic manure, your return will be in 5 years. So this is up to 50 kilo. And we have also installed a large capacity. So this is one installation we did for the Trivandrum International Airport. The entire food waste from both the domestic and international terminal is treated in this system, which is around 500 kilo food waste per day. With these, the unit we installed in 2000. We operated the plant for nearly 1 year and we handed over to the airport authority. So the inside plant look like this. We have a couple of 2 parallelly operating digester units, each one treating 250 kilo per day. Whatever biogas produced is stored it here. So the biogas we are purifying here and upgrading the methane percentage, not up to 90%, up to 65%, I mean 70%. And since the biogas usage is not at this point, what we were doing here is we were converting that into electricity. And whatever power produced, we are using for local light. So the compact size, no freshwater consumption, scalability. Scalability means So suppose today they have only 500 kilo per day, and tomorrow suppose they have more food waste. So the basic structure remains the same. They only need to add these bioreactors. Even they can stack one above the other. So that is what I mentioned by the scalability. You can scalable up to 1 ton or even beyond that. The basic, all other structure remains the same. Scalable, it can take any food waste, less slurry out, highly stable system, even large unit can be portable. You can move it from one place to another, particularly the 50 kilo system. You can move it even while it is working. And it also yield more biogas. And there are no mosquitoes or similar vector problems. So I'll skip this slide because of the paucity of time. So that was about the solid waste management. And I'll pass on to the liquid waste management, particularly the community waste treatment. And if you look at the daily water usage in different countries, an Indian in urban area, as per the calculations, it uses around 135 liters per day. Whereas in rural village area, it will be something like 45 to 50 liter per day. And when you compare this water consumption to an American, his daily water usage is something like 550 liters. So 550 liters water doesn't mean that he's using 550 liters for fresh water. So whatever water he has used, he'll be treating it and he'll be reusing it actually. So at a household level, 80% of the water you're using will be disposing in wastewater. And one thing you should understand, whatever wastewater from your kitchen, your bathtub, or your washing machine, all those things collectively called as grey water. It is also called as sewage, but sewage, the word usage is nowadays not there. We call them as grey water. And the other wastewater is from the toilet, which we call it as black water. So the black water and grey water together, we call it as sewage. This is what we discharge from our houses. Now in cities, we have houses with sewerage network. So the city, all the places may not be connected with the sewerage network, but the main part of the city in major cities will have the sewerage network. So from individual houses, you have the sewerage network. And you may also have pumping stations in it and manholes, of course, you may be knowing. So the sewerage line finally ends up with a common sewage treatment plant. And the sewage undergoes treatment here. And the treated water meeting the discharge standards, either you can dispose it or we can take it for different reuse applications. Like for construction purpose, you can use it for service stations, you can use it for different industrial needs. You can also consider it for horticulture or agriculture, especially for maintaining the city greenery and all those things. But suppose there is another scenario in which a large number of houses without any sewerage connection. This is a situation in many cities, and in rural area, definitely they don't have any sewerage connection. And how do they manage their wastewater? Of course, the black water will be directly going to the septic tank or pit latrines, whatever it is. And how about the grey water? So if you look at the wastewater disposal from a house, so 25% of the wastewater will be black water, which is directly going to the septic tank or pit latrine. And 75%, which we call the grey water or the sewage, which is directly we are disposing into so-called soils. And the septic tanks, these are the kind of septic tanks nowadays we follow. The functioning of these kind of septic tanks are a bit doubtful. But anyway, so we are adopting those kind of systems. And the overflow from these kind of septic tanks, and we are least bothered about, or we may use some kind of soft pit which are not safe to dispose those kind of wastewater. And how about this fecal sludge? So those kind of things are, we're not going to the details of those things. I just wanted to pose those questions to you. And coming to the grey water, this is a very common practice. We used to make a sock pit and we directly nearly 75% of the grey water into the sock pit, and which can directly contaminate our groundwater. So the discharge of untreated or poorly treated sewage accounts to 70% is the major cause of deterioration of our surface and groundwater quality. And emerging issues like the antibiotic resistance and related public issues are there. Now, houses without sewerage network, how do we address this problem? So can we consider something like this? A couple of houses together, we can have a treatment system. So this will avoid the problem of establishing elaborate sewerage network in cities without sewerage. So this is one option before us. We can have a treatment system for a couple of houses together, and the treated water we can reuse for different applications, at least for the external application, so that we can bring down the freshwater consumption at household level. Or can we consider treatment system for individual houses, at least for the grey water? So this is what is meant by the decentralized treatment system or on-site treatment system. That means we are treating the wastewater at the source of its origin. It can also called as non-sewer sanitation system. We are not connecting to the sewerage system. Or it is also called as the off-the-grid treatment system, something similar to the grid system of KC. So all the same. And there is another issue. I'll skip this because of the time. Now, if you consider sewage, every 1,000 liter of sewage will have carbon in it as a contaminant, will have some nitrogen, will have some phosphorus, sulfur, some micronutrients, all those things. And if you remove all those things, the remaining is nothing but water. Clean water, it can be reused. So if you have something like a resource-oriented treatment system, the sewage can be treated, different resources like reuse quality water, energy, and fertilizer can be recovered. And how do you do that? So this is how we mean by the term resource-oriented sewage treatment, or at least resource-oriented grey water treatment. So this is the general scheme for the treatment system. You can treat up to any level. You can treat up to potable quality. The sewage can be treated, and we can generate even potable water from out of that. But depends on the extent of treatment, the cost will definitely increase. So you can initially, at least you can remove the major contaminants, organic contaminants you can remove. Let the nutrients be there, and that water, you can use it for irrigation purpose, for agriculture purpose. And you can still remove the nutrient by installing some ion exchange resins and all those things. Once you remove those kind of contaminants, you can use the water for industrial or service stations. And still, as I mentioned, even if you remove all the micro contaminants, all the contaminants, and you can bring up to the potable quality. So most of these initial treatment systems or initial approaches that we follow are biological treatment systems, because of the nature-based treatment systems are more sustainable or more environment friendly. So if you look at the biological treatment systems, I mentioned biological systems are more sustainable and environment friendly. And if you look at biological treatment systems, mainly you can group them into two. One is a microbial process and another is the plant microbial process. Microbial process could be either aerobic process or anaerobic process. It depends on the kind of microorganism that you use. So I'll just speed up. And this table, it will be better you should just have a look at it. This shows about the carbon and energy balance of the aerobic and anaerobic microbial systems. And if you go for aerobic treatment systems, definitely you need to, it's an energy hungry process in the sense continuously you need to aerate the system. It's an energy intensive process, and you end up with carbon dioxide, and 50% of your organic contaminant is getting converted to biomass. That is nothing but sludge. It's another solid waste that you need to manage. But instead, if you go for anaerobic system, only 5% of your carbon is getting converted to biomass, and the rest 95% you'll be recovering as biogas. Similarly, the energy balance also. So why I'm telling all these things is that it depends on the nature of your wastewater. You either opt for anaerobic treatment system or aerobic treatment systems. So these are some of the examples of existing technology for on-site or decentralized wastewater treatment system, like the moving film bioreactor or MBBR technology, or the sequence bioreactor, SBR. Jokoso is a Japanese technology. DWATS is generic term for a decentralized wastewater treatment system. And Phytority is a plant microbial treatment system. And all these systems are not suitable for high-strength wastewater, like typically from a small hotel or restaurant or catering unit. These kind of wastewater cannot be treated by these existing technology, where you need to have other treatment technologies. So this is one technology that we work in this area. This is again a combined anaerobic aerobic treatment system, which is best suited for treating wastewater from small hotels, restaurant, catering units, and so on. And this is a combined anaerobic aerobic process unit with integrated sludge handling and disinfection modules also. You can see the photograph on the right side. The up photo is a 3,000 liter treating small unit, which is installed in a bakery unit. You can see the green balloon, which is filled with the biogas. So this system can recover both reuse quality water as well as biogas. And the bottom figure shows a 10,000 liter treating unit treating wastewater from a canteen. So these kind of systems can be implemented, and you remember this is system. I mean, this slide I have presented, and the problem with the grey water disposal. So can we come up with some kind of a treatment system for treating the grey water? So instead of disposing the wastewater in soak pit, can you come up with some kind of a treatment system? So whatever grey water, instead of putting them in soak pit, can we come up with a treatment system where the grey water can be treated at household level and the treated water can be reused at least for external purpose? So we developed something like this. This is a household grey water treatment system and reuse system. This is something like a small garden or something like that. This can function as a part of your garden. So the grey water we can directly introduce into this system. So this system need not be above the surface. This can underground also, only the top 1 feet or half a feet will be above the soil. So whatever grey water, the wastewater from your kitchen or whatever it is, you can directly feed in the system. That water, the treated water coming out of the system is safe to dispose. It's safe to dispose for groundwater charging, or you can use it for irrigating, watering your garden. So this is a community level treatment. The previous one was for individual houses, and this is for community. So this is one system functionally in our campus. So this is staff apartments, wastewater, all the grey water we pool together. We pass through an initial anaerobic system, followed by an eco-engineering system. We are generating the reuse quality water. So this is a photograph. So this is an eco-engineering unit. The way our apartments are here, wastewater initially goes some kind of treatment here. Then it passes through this plant microbial system. And you can see, so this is the inlet wastewater on the right side, and you can see the quality of the treated reuse quality of the, that can be reused for many purposes. I have a small video. I'll try to play it. I'm not sure whether it is going to play. Was not playing. So I'll pass on to my last part, how NIIST can support you people. So we used to organize many training programs and skill development programs, particularly in this sector, anaerobic digestion, wastewater treatment, all those sectors. We normally used to organize many training programs. You can frequently watch our website. You can join for these kind of programs that will help you in your capacity building in this sector. And if any of you have ideas or POCs, what you call the proof of concept or prototype, if you want to test it and if you want to validate it, you can come to us. We will help you. And if you have a technology or process testing and validation, we can do that. For example, organic waste converter or composting process units or microbial inoculum, all those things. If you want to test it, if you want to validate it, if you want to take it to the next level, we can help you in that one. And other option is co-development. If you have an idea, if you want to co-develop the technology or your product in a different level, if you need our help, we can do together. We can co-develop. You can use our infrastructure, our instrument facility, and all those things will be available. Okay. So just a recap of what we have discussed today. Initially, I talked about the sustainable energy, organic waste, the big picture of the SADA scheme, the Biogas Association India, all those things we talked initially. Then I mentioned something about the science of biomethanation, how organic waste is getting converted into biogas, what are the challenges in that sector, what are the options before you, what are the scope before you. Then we talked about wastewater treatment, particularly the on-site wastewater treatment system, community level wastewater treatment system. And finally, we also saw the household grey water, the emerging technologies or options for grey water treatment at household level. So with this, I'll stop here and I'll be happy to answer any questions. Thank you all. Thank you for your kind listening.
Thank you, sir, for that insightful session. Dear participants, the floor is now open for the question and answer session. So you can unmute yourself and ask your queries to sir.
Hello,
you can
good
even put your
evening.
question. Yes, sir. Continue, sir.
Good evening, doctor. Good evening, ladies and gentlemen. And
Yeah, good evening,
it
sir.
was a very good presentation. And now we understand from this whole talk, there is a huge amount of waste generated by us, and there is a tremendous scope of utilizing it. Now, how to utilize that? You have given many methods. Now, to every individual has to educated for this. Now, how much every individual get initiative in this? It is difficult to have 100%. Very few percentage may come forward. For this, our system has to generate some rules and regulation. Whenever we give a permission for a house construction, this has to be ensured and give the permission. Every panchayat level, this has to be ensured that they should implement this system, waste management. Now we can see, now I'm talking about the individual way where we stay, our own house, we have waste generated from, say, washroom. There are two types of waste generated, what you said, gray and black. Whereas in the washing machine, we have waste generated. From kitchen, we have waste generated by water as well as vegetables and vegetables. So everything finally it is going to the septic tank. So those things needs to be, as you said, needs to be segregated in a professional way and it has to be utilized. It's a great opportunity we have. But only thing this can be implemented through what I understand is, though individual take initiative, but there has to be a regulation. Legislative regulation must be there and make it compulsory. Then it is possible. There is a very, like solar energy, utilizing solar energy, there is now, it is very widely going on. This, when an individual is establishing a biogas unit, I have in our area many houses, it's abandoned, as you said, because of they do not know how to use it. And they one day, initially maybe using it in a better way, but later on, it all get abandoned. So it has to be monitored, yes, whether this is being used and how much gas is generated. Those monitoring system only can help this, what I understand. It's a very good presentation. It is very useful, and engineers should take initiative in this to take forward. That's all I want to say. And this video will be there in the YouTube. Yesterday I missed it. Yesterday was
Yes,
the same
sir, it
chapter
will
or
be
something
there on
different?
YouTube.
Yesterday was a different chapter, yeah. Okay, thank you.
Yeah.
And once again, thank you to the organizers for organizing this very good event. And thanks a lot. Thank you.
Thank you, sir.
Thank you, Babu sir. You can also put your questions in the chat box so we can take it up right now.
Hello, sir. നമുക്ക് previously കുറച്ച് questions വന്നിട്ടുണ്ടായിരുന്നു. അതിനകത്ത് ഒരു
Yeah,
question
yeah. No, you can ask the questions. You can ask in Malayalam also. Absolutely no problem.
Okay. Sir, വന്നൊരു question എന്ന് പറഞ്ഞാൽ, how can we ensure the safe disposal of hazardous waste materials?
In fact, at the beginning itself, I mentioned we are not talking about hazardous waste. In fact, hazardous waste എന്ന term തന്നെ വളരെ broad-ആണ്. അപ്പൊ അതൊരു എന്താ പറയുക, ചെറിയൊരു സ്റ്റേറ്റ്മെന്റ് കൊണ്ടൊന്നും നമുക്ക് കവർ ചെയ്യാൻ പറ്റത്തില്ല. ആക്ച്വലി എന്താണ് ഹസാഡസ്, ഈ ക്വസ്റ്റ്യൻ ചോദിച്ച ആള് എന്ത് ഹസാഡസ് വേസ്റ്റിന്റെ കാര്യമാണ് ഉദ്ദേശിച്ചത്?
സാർ അത് മെൻഷൻ ചെയ്തിട്ടായിരുന്നു previously. Even
Yeah, that's it. ഈ hazardous waste എന്ന് പറയുന്നത് തന്നെ വളരെ broad ആയിട്ടുള്ള ഒരു term. Biomedical waste is hazardous waste. Even consider the napkins in our houses, burning the napkins, diapers. These are all considered under the biomedical waste category. These are all cannot simply burn it actually. ഇതെല്ലാം ആ ഒരു കാറ്റഗറിയിൽ വരുന്നതാണ് actually.
Okay. നമുക്ക് ഒരു ചാറ്റിൽ ഒരു ചോദ്യമുണ്ട്. Can we
question
directly
in the
use
chat
food
box.
waste?
Yeah, please.
Continue, Kumaresh.
Oh, okay. Can we directly use food waste as feedstock?
Yeah, definitely.
Okay. Next one
Food waste
how
is a
can
very
we-
good substrate for biogas plant because it's highly balanced. The carbon nitrogen ratio is very good, and you will get a lot of biogas. As I mentioned, if you follow the dry anaerobic digestion, up to 200 liter, even above 200 liter, we have instances where above 200 liter per kg wet waste can expect.
Sir, next question is how can we reduce the moisture content?
Moisture content
Sir,
of what?
ഫീഡ്സ്റ്റോക്കിന്റെ ഇപ്പം ചോദിച്ചിരുന്നല്ലോ, അതിന്റെ കണ്ടിന്യൂഷൻ ആയിട്ട് ചോദിച്ചാണ്.
Moisture content of
ഫുഡ് വേസ്റ്റ് നമുക്ക് ഫീഡ് സ്റ്റോക്ക് ആയിട്ട് യൂസ് ചെയ്യാമെന്ന് ചോദിച്ചല്ലോ. അപ്പൊ അതിന്റെ മോയ്സ്ചർ കണ്ടന്റ് ആണ് റെഡ്യൂസ് ചെയ്യുന്നത് എങ്ങനെയാണ്?
മോയ്സ്ചർ കണ്ടന്റ് റെഡ്യൂസ് ചെയ്യുന്നത് വെച്ചാൽ നോർമലി നമ്മുടെ ഏരിയയിലുള്ള ഫുഡ് വേസ്റ്റ്, നമ്മൾ നോർമൽ വേസ്റ്റ് മെറ്റീരിയൽ ഫുഡ് വേസ്റ്റ് ആസിഡ്സ് ആയിട്ട് നമ്മൾ കൺസിഡർ ചെയ്യുകയാണെങ്കിൽ അതിലൊരു 75% ആവറേജ് 75% മോയ്സ്ചർ ഉള്ളതാണ് ആക്ച്വലി. അപ്പൊ അതുകൊണ്ടാണ് നമ്മൾ ഈ ഡ്രൈ എൻഡോബിക് ഡൈജഷനിൽ അതിന്റെ കൂടെ നമ്മൾ എക്സസ് ആയിട്ട് വാട്ടർ ആഡ് ചെയ്യേണ്ട കാര്യമില്ല. ഈ പറയുന്ന 75% മോയ്സ്ചർ ഈസ് മോർ ദാൻ ഇനഫ്. അപ്പൊ അതിൽ പിന്നെ ഇഫ് യു വാണ്ട് ടു റെഡ്യൂസ് ദ മോയ്സ്ചർ കണ്ടന്റ് സ്റ്റിൽ ഡ്രൈയിങ് മാത്രമേ ഓപ്ഷനും, അതല്ലാതെ അല്ലെങ്കിൽ യു ഹാവ് ടു യൂസ് സം കൈൻഡ് ഓഫ് മെക്കാനിക്കലി സ്ക്യൂസ് ഔട്ട് എക്സസ് വാട്ടർ, അതൊക്കെ മാത്രമേ. Otherwise you cannot remove the moisture. And I don't understand the scenario where you want to remove the moisture content.
The next question is, can we use dried and grinded bio waste as fertilizer?
Sorry?
Can we use dried and grind bio waste as a fertilizer?
Again, the term bio-waste is very ambiguous. എന്താണ് ഈ bio-waste എന്ന് ഉദ്ദേശിക്കുന്നത്?
I'm not sure about it. I think Tawhida has posted that question. If there's a better, yeah, it's on organic waste. She meant organic waste.
Dried organic waste.
Dried and grinded organic waste.
As a
Can we
fertilizer.
use that as a fertilizer?
Yeah, it can be used actually, provided if it's not smelling badly, because there's a kind of composting called the bokashi composting, in which you are subjecting your waste material, let it be food waste, into an anaerobic condition where some kind of a fermentation happens actually, in presence of lactobacillus kind of thing, or half pickling effect ആയിരിക്കും, അല്ലെങ്കിൽ ഒരു ഫെർമെന്റേഷൻ ആയിരിക്കും നടക്കുന്നത്. അതിന്റെ ഒരു pH ഡ്രോപ്പ് ആയിട്ട് ഒരു ഹാഫ് ഫെർമെന്റഡ് സ്റ്റേറ്റിലായിരിക്കും. അത് നമ്മൾ ആസിഡ് ആയിട്ട് ഫർദർ അതിന്റെ ക്യൂറിങ് നമ്മൾ ചെയ്യുന്നത് അത് ആസിഡ് ആയിട്ട് നമ്മൾ ലാൻഡിൽ ബറി ചെയ്യാണ് ചെയ്യുന്നത്. അപ്പൊ അതിന്റെ ഒരു എന്താ പറയുക, ന്യൂട്രിയൻ വാല്യൂ ഒന്നും ലോസ് ആവാതെ തന്നെ ഡയറക്റ്റ് ആയിട്ട് പ്ലാന്റ്സിന് അത് അബ്സോർബ് ചെയ്യാവുന്നതാണ്. Instead of directly grinding and drying and grinding and disposing, this can be a better option. കുറച്ചുകൂടെ ഡൈജസ്റ്റഡ് ഫോമിലായിരിക്കും അതിന്റെ ന്യൂട്രിയൻ വാല്യൂ ന്യൂട്രിയൻസിന് ഈസി ആയിട്ട് പ്ലാന്റ്സിന് അബ്സോർബ് ചെയ്യാൻ പറ്റുന്നത്.
This would still be under aerobic conditions, right?
ഞാൻ ഈ പറഞ്ഞതോ, ഈ ബൊക്കാഷി കമ്പോസ്റ്റിംഗ് എന്ന് പറയുന്നത് അനറോബിക് ആണ് ആക്ച്വലി.
ഇതിന് ലീച്ചേറ്റ് ഫോർമേഷൻ വല്ലാത്തൊരു പ്രശ്നമാണ്.
ലീച്ചേറ്റ് ഉണ്ടാവാം, ബൊക്കാഷിയില് ലീച്ചേറ്റ് ഉണ്ടാവാൻ ചാൻസ് ഉണ്ട്. അത് ഒരു ലിക്വിഡ് ഫെർട്ടിലൈസർ ആയിട്ട് കൺസിഡർ ചെയ്യാവുന്നതാണ്.
Okay. The next question is, can we go for mechanical grinding process to increase the efficiency?
Definitely, that's a good thing. In fact, നമ്മുടെ കൺവെൻഷണൽ ബയോഗ്യാസ് പ്ലാന്റിൽ പലപ്പോഴും ഈ വേസ്റ്റ് മെറ്റീരിയൽ കംപ്ലീറ്റ് ആയിട്ട് ഡൈജസ്റ്റ് ചെയ്യാത്തതും ഡിസ്ചാർജിലായിരിക്കും സ്മെൽ ഉണ്ടാവാനും ബയോഗ്യാസിന്റെ അളവ് കുറയാനും ഒക്കെ ഒരു മേജർ റീസൺ എന്ന് വെച്ചാൽ നമ്മൾ ലംസ് ഓഫ് വേസ്റ്റ് മെറ്റീരിയൽ ആസിഡ് അതിലേക്ക് ആഡ് ചെയ്യുന്നത്. അപ്പോൾ നമ്മൾ മെക്കാനിക്കലി ഗ്രൈൻഡ് ചെയ്ത് അതിന്റെ പാർട്ടിക്കിൾ സൈസ് റെഡ്യൂസ് ചെയ്തിട്ടാണ് നമ്മൾ ആഡ് ചെയ്യുന്നതെങ്കിൽ what happens is that the surface area കുറയ്ക്കുന്നതുകൊണ്ട് എൻസൈം ആക്ടിവിറ്റി അല്ലെങ്കിൽ മൈക്രോബിയൽ ആക്ടിവിറ്റി കുറേ എഫക്റ്റീവ് ആയിട്ട് നടക്കും. കുറച്ചുകൂടെ കൂടുതൽ ബയോഗ്യാസ് ഉണ്ടാവാനും ബയോഗ്യാസിന്റെ പെർഫോമൻസ് സ്റ്റേബിൾ ആയിട്ടിരിക്കുകയാണ്, അത് നല്ലതാണ്. ഡെഫിനറ്റ്ലി നല്ലത്.
നമ്മുടെ ഈ വീടുകളിൽ ഇൻസിനറേറ്റേഴ്സ് വാങ്ങിച്ച് ഉപയോഗിക്കാനായിട്ടുള്ള ഓപ്ഷൻസ് ഉണ്ടല്ലോ. യൂഷ്വലി അതിന്റെ പ്രോബ്ലം എന്താണെന്ന് വെച്ചാൽ അതിന് ആക്ച്വലി ഫണൽ ഉണ്ടാവും. But at the end of it, adinu varuna gas motham is released back to the atmosphere itself. So, is there an alternative mechanism wherein we can convert that particular gas itself into something different, so that there is no more emissions happening?
And one thing we should understand is we are not supposed to operate these kind of non-scientific equipments.
Okay.
എന്താ പറയാ, യാതൊരു സയന്റിഫിക് ബേസിസും ഇല്ലാതെ ആൾക്കാർ മാർക്കറ്റിൽ ഇത്തരം ഒരുപാട് സാധനങ്ങൾ അവൈലബിൾ ആണ്. അതൊന്നും നമ്മൾ ഓപ്പറേറ്റ് ചെയ്യാൻ പാടില്ല. ദ ഓൺലി തിങ് ഇസ് ദാറ്റ് ദ പ്രോബ്ലം ഈസ് ദാറ്റ് നമ്മളിതിനകത്ത് എന്തൊക്കെയാണ് ബേൺ ചെയ്യുന്നത് നമ്മൾ നോക്കുകയാണെങ്കിൽ പേപ്പർ, പ്ലാസ്റ്റിക് അലോങ് വിത്ത് വെറ്റ് വേസ്റ്റ് ലൈക്ക് ഫുഡ് വേസ്റ്റ് എല്ലാം കൂടെ ഒരുമിച്ചിട്ടായിരിക്കും നമ്മൾ കത്തിക്കുന്നത്. ആൻഡ് ഓഫ് ഗ്യാസിൽ ഡെഫിനറ്റ്ലി ഹൈലി ടോക്സിക് ആയിട്ടുള്ള ഒരുപാട് ഗ്യാസസ് ഉണ്ട്. അതുകൊണ്ടാണ് നമ്മൾ ഇത്തരം ലോ ടെമ്പറേച്ചറിൽ നമ്മൾ കത്തിക്കുന്നത്. ലോ ടെമ്പറേച്ചർ എന്ന് വെച്ചാൽ നോർമലി നമ്മൾ ഇൻസിനറേറ്റേഴ്സ് റെക്കമെൻഡ് ചെയ്യാറുണ്ട് ദാറ്റ് വിൽ ബി ഓപ്പറേറ്റിംഗ് അറ്റ് ഹൈ ഡിഗ്രി ടെമ്പറേച്ചർ ലൈക്ക് 700, 800 അതിന് മുകളിൽ ടെമ്പറേച്ചറിൽ മാത്രമേ നമ്മൾ ഇത്ര ഇൻസിനറേറ്റർ ഓപ്പറേറ്റ് ചെയ്യാവൂ. തന്നെയല്ല, ആസ് പെർ എക്സിസ്റ്റിംഗ് സോളിഡ് വേസ്റ്റ് മാനേജ്മെന്റ് റൂൾ ഇൻസിനറേറ്റേഴ്സ് എല്ലാം ഡബിൾ ചേമ്പേർഡ് ആയിരിക്കണമെന്ന്. ഇതിന്റെ പർപ്പസ് തന്നെ ഇത്തരം ഓഫ് ഗ്യാസസ് എന്താ പറയാ അതിനകത്തുള്ള ടോക്സിക് കണ്ടാമിനൻസ് എല്ലാം റിമൂവ് ചെയ്യാൻ വേണ്ടി. അതല്ലാതെ നമ്മൾ ഈ നോർമലി മാർക്കറ്റിൽ കാണുന്ന സിംഗിൾ ടെമ്പേർഡ് ഇത്തരം സാധനങ്ങളൊന്നും നമ്മൾ വീട്ടിൽ വെച്ച് ഉപയോഗിക്കാൻ പാടില്ല. Paper, plastic, you can recycle it actually. Nowadays, systems are in place where you can recycle these kind of things. And the wet waste, either you go for composting or you go for some kind of anaerobic digestion. That should be the practice we should be doing.
Okay. Do we have any more questions? I think so, because the time has exceeded.
Okay.
So I think we could wind up for today.
Yeah.
So thank you once again, sir, for taking up our invite and joining us today to give this such an insightful session on solid and liquid waste management and as well as disposal. I'm sure the students would have got a real good idea on how exactly we could ideate in this particular area, and I'm sure you can help out further, especially in research areas, being from CSIR and NIIST. So once again, thank you, sir, on behalf of KDISC and all the participants out here. Thank you, sir. Thank you, sir.
Thank you all.
Thank you.
Thank you, sir.
Thank you.